The distance that isn't empty. There is a photograph. You may have seen it without knowing what you were looking at. It shows two objects that are clearly related. They share a brightness, a scale, a kind of mutual orientation. And both of them are wrong in a way that takes a moment to identify. The wrongness is in the shapes. Each object has arms extending from it, but the arms don't follow the clean logarithmic spirals of a normal galaxy. They are pulled out, elongated, reaching in directions that suggest something external is acting on them, some force that is bending what would otherwise be a self-contained rotational system into something asymmetric and strange. This is the Antennae Galaxies, two spiral galaxies roughly 45 million light-years from Earth, caught mid-collision. The image has existed in various forms since ground-based observations in the mid-20th century, and in its sharpest form from Hubble observations beginning in the 1990s. It has been reproduced widely. It appears in textbooks and magazines and the kind of coffee table books about space that people buy when they want to feel something without committing to understanding it. But even if you have seen it, the odds are good that you processed it as a picture of something beautiful and moved on. The actual content of the image, what it is describing physically, and what the description implies about the nature of matter and time and the scale of events, takes longer to absorb than any single viewing allows. This video is the longer absorption. You're somewhere at this hour that is quiet, or nearly quiet. The sounds in the room, if there are any, are the kinds of sounds that register as background. The particular texture of a building at this hour, the distant sound of something outside, the sound of your own breathing if you're paying attention to it. These sounds exist because molecules are moving, air pressure waves are propagating. The electromagnetic force is doing its work at the surface of every object in the room, preventing solid things from passing through each other, giving the world its familiar impenetrability. None of this applies between stars. The space between stars is not like the space between objects in a room. The space between stars is almost entirely free of matter. Not free in the way a cleared room is free, not empty in any human-scale sense, but free in a way that makes any human-scale emptiness look crowded. The interstellar medium, the gas and dust that fills the space between stars in a galaxy like the Milky Way, has an average density of approximately 1 hydrogen atom per cubic centimetre, 1 atom per cubic centimetre. The best vacuum achievable in a laboratory on Earth, the kind produced in particle accelerators and ultra-high vacuum chambers, contains thousands of times more particles per unit volume than the average interstellar medium. The galaxy is less dense than anything we can manufacture. Given this, what happens when two galaxies collide? The intuitive answer for most people is something like an explosion. Two enormous structures of stars slamming into each other at some enormous speed, producing an enormous event. The intuition imports the physics of collisions at human scales, rocks hitting rocks, cars hitting cars, and scales it up to galactic dimensions. This intuition is wrong in almost every specific detail, because the galaxy is almost entirely empty space, and because the stars within it are separated by distances that dwarf their own sizes by many orders of magnitude. The probability of any two individual stars directly colliding during a galactic merger is extremely small. For a merger of two Milky Way-sized galaxies, the expected number of actual stellar collisions, surfaces touching, material exchanged, is close to 0 for any given star, and perhaps a handful across the entire population of hundreds of billions of stars. The stars, for the most part, do not touch. They pass through the space occupied by the other galaxy without coming anywhere near another star. And yet the shapes change, and yet the tidal tails form, and yet new stars are born by the millions in the collision zone, and yet the two central black holes, now separated by millions of light years at the start of the encounter, begin a journey toward each other that will take billions of years to complete. Something enormous is happening, but it is not an explosion in the sense your intuition constructed. It is something slower, larger, stranger, and in its own way more interesting. The something enormous is gravity. Gravity has no requirement for physical contact. It does not need two pieces of matter to be touching, or even close, to produce a significant effect. It acts across the void between stars and between galaxies, across distances that light takes millions of years to cross, and it does so with perfect consistency. The gravitational field produced by an object extends in principle to infinity, attenuating with the square of the distance, becoming very weak at large distances but never reaching zero. When two galaxies begin to approach each other, when the separation between them decreases to the point where their mutual gravitational attraction becomes significant relative to their velocity, the process begins. Nothing visible marks this beginning. No signal propagates from either galaxy announcing that the interaction has commenced. What changes invisibly is the motion. Each galaxy begins to accelerate very slightly toward the other. The acceleration is tiny. The distances are enormous. The timescales over which this initial, barely perceptible mutual attraction will produce any visible consequence are themselves enormous. Many millions of years just for the acceleration to accumulate enough to detectably alter the galaxy's courses. This is how galaxy collisions begin, not with a bang. With a barely measurable change in velocity, distributed across a system the size of 100,000 light-years, operating over timescales that make the entire history of multicellular life on Earth look brief. The Milky Way is going to collide with the Andromeda Galaxy. This is one of the most well-supported predictions in modern astrophysics, and it deserves to be stated plainly before being elaborated on. The Andromeda Galaxy, the spiral galaxy visible as the faint oval of light in the constellation Andromeda, the most distant object visible to the naked eye under good conditions, a smear of light that requires roughly the area of 6 full moons to span and that contains approximately 1 trillion stars, is moving toward the Milky Way at approximately 110 kilometers per second. This motion has been measured precisely enough, using the Hubble Space Telescope and later the Gaia mission, to determine that Andromeda is on a collision course with our own galaxy. The collision is expected to begin in approximately 4 to 5 billion years. That number, 4 to 5 billion years, sits comfortably enough in a sentence. It can be read aloud without difficulty. But it resists absorption in the way that most large numbers resist absorption. 4 billion years is longer than the Earth has existed. It is longer than the sun has been burning. It is long enough that the continents will have moved to configurations that make current geography unrecognizable. Long enough that the species now alive will be as remote from whatever biology then exists as the Cambrian fauna are from us. Long enough that almost nothing that currently exists will exist in a recognizable form, with the possible exception of stars, which age slowly enough to still be present, though in advanced stages of their own evolution. 4 billion years, and then Andromeda arrives. But this event, dramatic as it is when described in isolation, is not unusual. It is in fact one of the routine processes of cosmic evolution. Galaxy mergers are not exceptional. They are how large galaxies become large. The Milky Way itself has merged with smaller galaxies in its past, and the evidence is visible in the structure of the stellar halo, the diffuse cloud of old stars surrounding the galactic disk, which contains debris streams and disrupted remnants of galaxies that the Milky Way absorbed billions of years ago. The Sagittarius dwarf galaxy is currently being absorbed. It has already been significantly disrupted by the Milky Way's tidal forces, and its stars now trace a long stream around the galaxy, looping over the poles in a structure that was discovered in the early 2000s and has been mapped in increasing detail since. The Gaia mission, which measured the positions and velocities of about 1 billion stars with unprecedented precision, has revealed that the Milky Way's stellar halo contains multiple streams and substructures consistent with past merger events, some of which have been given names like Gaia Enceladus or Gaia Sausage, based on the velocity structure of the stars they contributed. The Milky Way is a galaxy that has eaten other galaxies. It will eat Andromeda and be eaten by it. The merger is mutual, producing a single system from two, and the result will be something that looks nothing like either progenitor. What the result looks like is an elliptical galaxy. The Milky Way and Andromeda are both spirals, disc-shaped, rotationally supported, with ongoing star formation and prominent spiral arm structure. The merged system, sometimes called Milkomeda in popular writing, a portmanteau that appears in no formal literature but that captures the idea accurately, will be an elliptical galaxy. Smooth, featureless in comparison to the spirals, supported not by rotation but by the random three-dimensional motions of its stars. Old and red, because the star-forming gas will have been largely consumed in the merger and subsequent quenching. The story of how two spirals become one elliptical is the story this video is about. It takes several billion years. It involves processes operating at every scale, from the quantum, the nuclear reactions inside stars that respond to changing stellar environments, to the cosmological, the dark matter halos that govern the overall merger dynamics. It produces some of the most luminous events in the universe, starbursts, active galactic nuclei, and also some of the quietest, stellar orbits modified by a fraction of a percent over millions of years. The story is worth telling in full. Let's start with what the photograph is actually showing. The antennae galaxies, named for the long tidal tails that extend from both systems and that reminded the astronomer Fritz Zwicky, who first noted the unusual morphology, of the antennae of an insect, are two spiral galaxies designated NGC 4038 and NGC 4039. They are approximately 45 million light-years away in the constellation Corvus, and they have been in their current state of interaction for roughly 600 million years. The two nuclei are still distinct, visible as two separate bright cores in the images, and the tidal tails extend for hundreds of thousands of light-years in each direction. Between and around the nuclei, the collision zone is lit with star-forming regions, compact clusters of new, massive, hot blue stars that did not exist before the collision began. The antennae represent one particular moment in the long sequence of a galactic merger. They are after the first pass. The two galaxies have already passed through each other once, and they are now in the process of falling back together for the second pass and eventual final merger. The shapes we see in the images are the accumulated result of 600 million years of tidal interaction and gravitational dynamics. 600 million years is roughly when the Cambrian explosion happened on Earth. When the antennae first began their interaction, the most complex life on this planet was microbial. The entire history of complex animal life has occurred in the time it has taken the antennae to reach their current state. The image of the antennae, then, is not a picture of an event. It is a picture of a process, one frame in a sequence that spans hundreds of millions of years. The wrongness of the shapes is not damage, it is information. The distorted arms, the tidal tails, the star-forming knots, all of these are the gravitational field of the encounter writing itself into the visible matter of both galaxies, recording the history of the interaction in a language that astronomers have learned to read. The chapter that follows will build the vocabulary for reading that language. What makes a galaxy's shape? What happens to that shape when another galaxy's gravity begins to act on it? Why the stars move the way they move? Why the gas behaves so differently from the stars? Why new stars are born in the collision? Why the black holes in the centers of both galaxies will eventually find each other? All of it is gravity. Gravity at scales and time scales that the word gravity was never really designed to convey. One more thing before moving on, because it is relevant to everything that follows. The Milky Way is not at the center of anything. This is not a philosophical statement about cosmic significance. It is a positional fact about where we are in the large-scale structure. The Milky Way is a member of the Local Group, a collection of roughly 80 galaxies, most of them small dwarf galaxies, bound gravitationally into a structure approximately 10 million light-years across. The Local Group is itself a member of the Virgo supercluster, which is in turn a lobe of the even larger structure called Gaia, which contains something like 100,000 galaxies and spans roughly 500 million light-years. The Milky Way sits near the edge of the Local Group, near the edge of the Virgo supercluster, near the edge of Gaia. We are peripheral to multiple structures simultaneously, and Andromeda is our closest large neighbour, the only galaxy of comparable mass in the Local Group, and the dominant mass concentration in the half of the Local Group on its side of the divide. The collision is between the two most massive members of the Local Group. When it happens, the resulting merged galaxy will be the dominant object in the Local Group, a position Andromeda currently holds because it is slightly more massive than the Milky Way. The merged system will eventually absorb the smaller members of the Local Group as well. The Magellanic Clouds, the dwarf spheroidals, the irregular satellites. What remains, on timescales of perhaps 100 billion years, will be a single large elliptical galaxy in an increasingly empty region of the universe, as dark energy continues to accelerate the expansion and drive other galaxy groups over the cosmological horizon. But that is much later. Right now, or rather, in 4 to 5 billion years, the first pass. Before the collision can be understood, the thing being collided needs to be understood. What a spiral galaxy actually is, not in the sense of a photograph or a shape, but in the sense of a physical system, a set of components held together by specific forces at specific scales, each component responding to the merger dynamics differently. A spiral galaxy is not a solid object. It is not a disk in the way a frisbee is a disk, a coherent structure that moves as a unit. It is a system of largely independent objects, stars, gas clouds, dust, dark matter. each pursuing its own orbit around the common centre of mass, with the spiral arm structure being a pattern that moves through the stellar population rather than being carried by it. The stars in a spiral arm are not the same stars that were there the last time a given arm swept through that region. The arm is a density wave, a region of enhanced density that propagates through the stellar population, triggering star formation as it compresses the interstellar gas. This distinction matters enormously for understanding what a merger does. The disk of the Milky Way is approximately 100,000 light-years in diameter. The Sun is located about 26,000 light-years from the centre, roughly 2/3 of the way out from the centre to the outer edge. The disk is relatively thin. The scale height of the thin disk is about 1,000 light-years, meaning that most of the disk's stars are within 1,000 light-years of the midplane. The outer disk becomes warped and flared, extending significantly above and below the plane at large radii. A feature common to most disk galaxies and thought to result from past interactions and the influence of the dark matter halo. The stellar disk contains approximately 100 to 200 billion stars, with the uncertainty driven primarily by the difficulty of counting stars in the inner galaxy through the obscuring dust lanes. The disk also contains the interstellar medium, the gas and dust from which new stars form. The interstellar medium is concentrated in the spiral arms, with molecular clouds of cold, dense gas, temperatures of 10 to 30 Kelvin, densities of 100 to 1,000 atoms per cubic centimetre, sitting in regions that are also the sites of star formation. The total mass of the interstellar medium in the Milky Way is roughly 10 to 15% of the total stellar mass, a significant but minority component. The bulge is the central, roughly spheroidal component of the galaxy. In the Milky Way, the bulge is actually a bar, an elongated rotating structure rather than a pure spheroid, which is why the Milky Way is classified as a barred spiral galaxy. The bar is roughly 27,000 light-years long and drives gas inflow toward the centre through non-circular orbital dynamics. The supermassive black hole at the centre, Sagittarius A star, with a mass of approximately 4 million solar masses, sits at the very centre of the bar. The halo is the most diffuse component and, in terms of mass, potentially the most important. The stellar halo contains relatively few stars, old metal-poor stars on highly eccentric orbits that take them far above and below the galactic plane. But the dark matter halo extends far beyond the visible galaxy in all directions, to distances of perhaps 500,000 to 1 million light-years. The dark matter halo of the Milky Way contains roughly 1 trillion solar masses of dark matter, about 5 to 6 times the total mass of all the stars and gas in the galaxy combined. This is the structure that Andromeda will encounter. Not just the visible disk, the disk that photographs show, the disk that contains all the familiar features of a spiral galaxy, but the enormous dark matter halo that envelops it, the stellar halo that records past mergers, the bar and bulge at the centre, and the supermassive black hole at its very core. Andromeda is larger. This is important and somewhat counterintuitive, because in the sky, Andromeda's disk subtends a larger angle than the Milky Way's appears to from outside. Andromeda is just over 2 degrees across, which is several times the angular diameter of the full moon, but the Milky Way and Andromeda appear roughly comparable in photographs. In reality, Andromeda has a stellar disk roughly twice the diameter of the Milky Way's, contains approximately 1 trillion stars compared to the Milky Way's 100 to 400 billion, and has a central black hole of roughly 100 million solar masses, about 25 times the mass of Sagittarius A star. Andromeda also shows more evidence of past mergers in its stellar halo. The halo of Andromeda is extraordinarily rich in substructure. Stellar streams, shells, and overdensities that betray a history of absorbing numerous smaller galaxies over its lifetime. The most prominent feature is the giant stellar stream, a long arc of stars wrapping around Andromeda's southern halo, which is thought to be the disrupted remnant of a massive satellite galaxy that Andromeda absorbed relatively recently. The Andromeda Galaxy has been eating its neighbours more aggressively than the Milky Way has, and its halo reflects this history. When these two systems meet, both already bearing the scars of past mergers, both carrying supermassive black holes at their centres, both embedded in dark matter halos that extend far beyond their visible disks, the interaction will be the most significant gravitational event in the local group's history. Gravity is the only force that matters for a galaxy merger, not electromagnetism, not the strong or weak nuclear forces. Gravity. Everything that happens during the merger, the tidal distortions, the orbital changes of individual stars, the gas compression that triggers star formation, the slow in-spiral of the central black holes, is a consequence of gravity operating simultaneously at every scale, from the separation of the galaxies as wholes down to the encounter of individual stars. This multi-scale character of gravitational dynamics is what makes galaxy mergers so rich and so computationally demanding. You cannot simply calculate the motion of the galaxies as point masses. The details of the mass distribution within each galaxy matter for the shape of the tidal features and the rate of energy dissipation. You cannot ignore the behavior of the gas. It responds to compression differently from the stars and produces feedback through star formation that in turn affects the merger dynamics. And you cannot ignore the dark matter, which provides most of the mass and therefore most of the gravitational field, but which interacts with itself and with ordinary matter only through gravity. The most immediate gravitational effect as the galaxies begin to approach each other is tidal distortion. Tidal forces arise from the gradient of the gravitational field, the difference in the gravitational pull on one side of an extended object compared to the other side. This side of the Milky Way facing Andromeda will experience a slightly stronger pull toward Andromeda than the far side will, and this differential pull will tend to elongate the Milky Way along the line connecting the two galaxies. For stars in the outer disk, this tidal distortion is significant. The outer stars are only weakly bound to the galaxy. Their binding energy is small because they are far from the dense central region, and because the dark matter halo's gravitational pull weakens at large radii. A relatively modest tidal perturbation from Andromeda is enough to send these stars onto significantly different orbits. Some will be stripped entirely from the Milky Way and enter orbits around the merged system's centre of mass. Others will be drawn out into the long tidal tails that are the most visually dramatic signature of a galaxy merger. The tidal tails form over timescales of hundreds of millions of years. They are not instantaneous. Each star in the tail is on its own orbit, modified by the tidal interaction, and the collection of modified orbits produces the tail as a spatial structure. The shape of the tail encodes the history of the interaction, the velocity of the encounter, the masses of the galaxies, the timing of the close approach. in a way that can, in principle, be inverted to reconstruct the merger history from the tidal feature alone. Within the disk itself, the gravitational effect of the approaching galaxy is subtler, but still significant. The disk is not rigid. It can be warped and thickened by tidal forces that act preferentially at certain positions. The existing spiral arm structure can be disrupted, new density waves induced. The bar at the center can be strengthened or weakened depending on the geometry of the encounter. For individual stars in the inner disk, stars at galactic radii similar to the Sun's, the direct tidal effect of the other galaxy is small during the early approach phase. The dominant gravitational influence on these stars remains their own galaxy's mass distribution. What changes for them initially is the large-scale potential. The overall shape of the gravitational field they are embedded in shifts slightly as the other galaxy's mass distribution adds to the background. This causes slow, secular changes in their orbits that accumulate over time, but not dramatic on any short time scale. The drama for inner disk stars comes later, during and after the first pass, when the gravitational potential of the merge system is reorganizing rapidly and orbital chaos becomes widespread. The gas is different. Gas cannot maintain ordered orbits when compressed. When the gas in one galaxy's interstellar medium encounters the gas in the other galaxy's interstellar medium, the interaction is not gravitational in the same clean way as the stellar interaction. Gas has pressure. Gas collides hydraulically, with shock waves propagating through the medium at the local sound speed. Gas that is compressed heats up unless it can radiate the energy away quickly, and whether it can do so depends on its temperature and density and composition. In the cold, dense molecular clouds, the sites of star formation, the gas can radiate efficiently and cool quickly even when compressed. This is fortunate because it means the compression drives the gas toward the conditions for gravitational collapse rather than preventing them. Warm diffuse gas takes longer to cool after compression and may not reach the collapse, rather than preventing them. Warm diffuse gas takes longer to cool after compression and may not reach the collapse threshold before the compression wave passes. The result is a spatially patchy distribution of star formation. Some regions of the collision zone producing stars furiously, others relatively quiescent. That reflects the pre-collision distribution of dense molecular clouds in both galaxies, combined with the spatial pattern of the compressional shock waves driven by the merger dynamics. And then there is dynamical friction. Dynamical friction is the gravitational drag experienced by a massive object moving through a background of lighter objects. As the object moves, it gravitationally deflects the background particles, creating an overdensity behind it, a gravitational wake that pulls back on the object, slowing it. The effect depends on the mass of the moving object, the density of the background, and the velocity of the motion. For a galaxy moving through the dark matter and stellar background of another galaxy, dynamical friction is the primary mechanism that dissipates orbital energy and drives the galaxies toward merger. Without dynamical friction, two galaxies that pass through each other would simply separate again and continue on their original trajectories, perhaps somewhat distorted but not bound. With dynamical friction, energy is removed from the orbit on each pass, bringing the galaxies closer together until they merge. The rate of energy dissipation by dynamical friction is proportional to the square of the object's mass and inversely proportional to the square of its velocity. This means that more massive galaxies merge faster, they experience more drag per unit mass, and that galaxies on slower, more nearly bound orbits merge faster than those on fast, nearly unbound orbits. The Milky Way and Andromeda, being the two most massive members of the local group, will merge relatively efficiently once the interaction begins. The current separation between the Milky Way and Andromeda is approximately 2.5 million light-years. Andromeda is approaching at approximately 110 kilometers per second in the radial direction, directly toward us, and has a transverse velocity component of roughly 17 kilometers per second in a direction that the Gaia mission measured with sufficient precision to determine that the encounter will be a nearly direct collision rather than a glancing blow, though the final determination of the impact parameter remains somewhat uncertain. At 110 kilometers per second, the light travel time to Andromeda is 2.5 million years, which means the Andromeda we see tonight is the Andromeda as it was 2.5 million years ago. The Andromeda of tonight's sky left its source before any human being had walked the Earth. It departed roughly contemporary with the first stone tools in the archaeological record. What Andromeda looks like right now, whether it has already begun to show tidal distortions from the approach, we cannot know. The information is in transit. The closing speed of 110 kilometers per second sounds fast in ordinary terms. It is about 390,000 kilometers per hour, far faster than any spacecraft humans have ever built. But at galactic distances, 110 kilometers per second is almost negligibly slow. At that speed, crossing the current 2.5 million light-year gap would take approximately 6.5 billion years. The current models predict a collision in 4 to 5 billion years, which means the galaxies are not moving at constant velocity but are being accelerated by their mutual gravity. The approach is speeding up as the separation decreases and the gravitational attraction strengthens. There is also the question of what the local group is doing as a whole. The local group is not expanding. Gravity holds it together against the cosmological expansion. The Milky Way and Andromeda are both members of this bound system, and their motion toward each other reflects the dynamics of the group rather than being a purely isolated two-body interaction. The smaller members of the local group, the dwarf galaxies, the satellite systems of both major galaxies, contribute to the overall gravitational potential and may slightly modify the merger timeline, though for the purposes of the dominant dynamics, the Milky Way-Andromeda interaction is well approximated as a two-body problem. The simulations of the Milky Way-Andromeda merger have been run many times with different initial conditions, different models for the dark matter halos, and different assumptions about the transverse velocity. The results consistently show a first close passage in the 4 to 5 billion year range, followed by a second passage and final coalescence roughly 2 to 3 billion years after that. The total duration from first contact to complete merger is expected to be in the range of 6 to 8 billion years from now. This means the merger will be underway when the Sun exits the main sequence, and will be complete, the two galaxies fully merged into a single elliptical, long after the Sun has evolved into a white dwarf and the inner solar system has been rearranged by the red giant phase. The approach, right now, is invisible to any observation. There is no signature in the current shapes of either galaxy that unambiguously reflects the ongoing gravitational interaction. The distance is too large, the time too short on the relevant scales. Andromeda shows the substructure in its halo from past mergers, and the Milky Way shows its own halo substructure, but neither shows evidence of the current approach in its morphology. The gravitational interaction has begun in the sense that both galaxies are accelerating toward each other, but the effects of that acceleration on the mass distributions are too small to be detected. What we detect instead is the velocity, the Doppler shift of spectral lines in Andromeda's light that tells us the galaxy is moving toward us, the proper motion measurements from Gaia that tell us the direction and speed of that motion, and the gravitational modelling that tells us what those measurements imply about the future trajectory. Measurement, calculation, prediction. The collision is not observed, it is inferred. And the inference, the certainty that in 4 to 5 billion years these two galaxies will begin to pass through each other, is one of the most confident long-term predictions in astrophysics. It is coming. Slowly, certainly at 110 kilometers per second, Andromeda is coming. Between the Sun and the next nearest star system, Alpha Centauri, approximately 4.24 light-years away, there is essentially nothing. The interstellar medium at this location in the Milky Way has a density of approximately 1 hydrogen atom per cubic centimetre, varying considerably depending on whether the line of sight passes through a diffuse region, a warm ionized region, or avoids the denser clouds of the spiral arms. By any human-scale standard, this is nothing. The Sun is approximately 1.4 million kilometers in diameter. Alpha Centauri is approximately 4.24 light-years, or about 40 trillion kilometers away. The ratio of the Sun's diameter to the distance to Alpha Centauri is roughly 1 to 28 million. If you put the Sun on one end of a football field, Alpha Centauri would be 28 million football fields away, somewhere in the outer solar system of a star 20 million kilometers distant. The stars are vanishingly small compared to the distances between them. Now scale this to a galaxy merger. The Milky Way contains somewhere between 100 billion and 400 billion stars. Let us use 200 billion as a reasonable estimate. Each star occupies a volume roughly comparable to its own diameter. The Sun's diameter of 1.4 million kilometers, other stars ranging from about 10% to 1,000 times this. The total volume of space occupied by the physical bodies of the stars, the stellar interiors, is negligible compared to the volume of the galaxy. The volume of the Milky Way's disk can be estimated crudely as a cylinder. 100,000 light-years in diameter, 1,000 light-years thick, giving a volume of roughly 7.8 billion cubic light-years. The volume of the Sun is approximately 1.4 times 10 to the 18th cubic kilometers, or about 1.6 times 10 to the negative 30th cubic light-years. 200 billion suns, each occupying 1.6 times 10 to the negative 30th cubic light-years, occupying a total volume of about 3 times 10 to the negative 19th cubic light-years. Divided by the total disk volume of 7.8 billion cubic light-years, the fraction of the galaxy's volume actually occupied by stellar material is on the order of 4 times 10 to the negative 29th. A fraction with 29 zeros after the decimal point before the first significant digit. The galaxy is not mostly empty. It is almost entirely, overwhelmingly, completely empty. The stars are points of matter in an ocean of vacuum so vast that their existence is statistically negligible from a volume perspective. This means that when two galaxies collide, when the 100,000 light-year disk of Andromeda interpenetrates the 100,000 light-year disk of the Milky Way, the probability of any given star in one galaxy directly colliding with any star in the other galaxy is extraordinarily small. The geometric cross-section of a star is tiny compared to the volume of space it is moving through. Two galaxies passing through each other are almost entirely two vacuums passing through each other, with occasional stars moving through the other galaxy's space without coming within many light years of any of the other galaxy's stars. Estimates of the actual stellar collision rate during a Milky Way Andromeda type merger suggest that the total number of stellar collisions, actual physical contact between the surfaces of two stars, across the entire event might be a handful, out of a combined population of perhaps 1 to 1.5 trillion stars, perhaps 0 for any given star. The collision is, from the perspective of an individual star's immediate environment, a non-event in terms of direct stellar encounters. What does collide, hydraulically and consequentially, is the gas. Gas is different from stars in a critical respect. Stars interact only through gravity at the separations typical of a galactic disk, but gas exerts pressure. Gas molecules, or in the hot phases of the interstellar medium, ions and electrons, interact electromagnetically as well as gravitationally, and when two gas flows meet, they interact through shocks, compressional waves propagating through the medium at the local sound speed, heating and compressing the gas on a timescale of millions of years. The interstellar medium of the Milky Way and Andromeda are both structured. Both contain diffuse hot ionized gas, temperatures of 1,000,000 degrees or more, warm neutral and ionized gas, temperatures of thousands to tens of thousands of degrees, and cold, dense molecular clouds, temperatures of 10 to 30 Kelvin, the coldest naturally occurring environments in the observable universe. The cold molecular clouds, despite being the smallest fraction of the interstellar medium by volume, contain most of the mass available for star formation. When two galaxies' gas disks interpenetrate, the cold clouds of one galaxy can encounter the cold clouds of the other. These encounters are hydraulic. The clouds collide, compress, shock heat, and potentially cool and collapse to form new stars. The rate at which this happens depends on the density and covering fraction of the cloud population, the relative velocities of the two disks, and the geometry of the encounter. Dark matter, as noted, is the dominant mass component, but dark matter's behavior in a merger is distinctly different from that of both stars and gas. Dark matter does not experience pressure. It is a collisionless fluid in the sense that individual dark matter particles interact only through gravity, not through any short-range forces. Dark matter halos, therefore, behave more like the stellar component than the gas component. They pass through each other, exchanging energy through gravitational interactions rather than through physical collisions. The dark matter halos of the Milky Way and Andromeda are already overlapping, or very nearly so. The virial radius of the Milky Way's dark matter halo is estimated at 200,000 to 300,000 light-years, and the same for Andromeda. At a current separation of 2.5 million light-years, the halos are not yet overlapping in any meaningful sense, but as the galaxies approach, the halos will begin to interact long before the visible stellar disks come close to each other. The dark matter halos will merge first, providing the dominant gravitational potential within which the stellar and gas components subsequently interact. One of the most striking direct demonstrations of dark matter's behavior in collisions comes from the Bullet cluster, two galaxy clusters that have already passed through each other. The hot gas of both clusters, which interacts hydraulically, was slowed and displaced by the collision, forming a bow shock between the two gas concentrations. The dark matter, which is collisionless, passed through the collision mostly unimpeded and is now offset from the gas by millions of light years, a displacement revealed through gravitational lensing of background galaxies. This offset provides direct evidence that dark matter is a real, physical component of galaxy clusters that behaves differently from the gas, and that cannot be explained by modifications to gravity. The same physics applies to galaxy mergers, though at somewhat different scales. The dark matter halos merge through dynamical friction, providing the gravitational framework within which the gas and stars interact. The moment of first contact, to the degree that phrase means anything at galactic scales, is not marked by any abrupt change. The tidal distortions begin long before the visible disks are anywhere close to each other, hundreds of thousands of light years before, as the outer stars of each galaxy begin to respond to the gravitational gradient produced by the approaching mass. The outer stars are the most vulnerable. They are the least tightly bound. Their orbital velocities are low, their binding energies small, their orbits large and slow. The tidal force from the approaching galaxy acts on them most strongly, because they are at the periphery of their own galaxy's mass distribution, where the local gravitational pull from home is weakest and the gradient from the intruder is largest. These stars respond first. Their orbits begin to change, not dramatically, not immediately, but measurably. Over millions of years, the accumulated effect of the tidal perturbation is to draw these stars out of their original disk orbits and into the beginnings of the tidal tail. The tidal tail is not a stream of stars moving in a single direction. It is a structure built from the collective response of many stars to many individual tidal perturbations, each star on a slightly different orbit that reflects the slightly different tidal force it experienced at its particular location in the disk. The coherence of the tail, the fact that it forms a single extended structure rather than a random scatter of deflected stars, reflects the coherence of the tidal force itself, which varies smoothly across the disk. As the approach continues and the separation decreases from hundreds of thousands to tens of thousands of light years, the tidal distortion of the inner disk becomes significant. The spiral arm structure of both galaxies begins to be modified. New density waves may be excited by the tidal forcing, producing additional spiral structure that is not intrinsic to the galaxy, but is driven by the encounter. In some simulations of galaxy mergers, the first passage actually temporarily enhances the spiral structure of both galaxies before the more dramatic disruption of the actual interpenetration. The encounter geometry matters critically for what happens during the first pass. A prograde encounter, in which the orbital angular momentum of the encounter is aligned with the spin angular momentum of the galaxy, produces longer, more pronounced tidal tails than a retrograde encounter, in which the angular momenta are anti-aligned. This is because in a prograde encounter, the tidal forces from the intruder galaxy remain aligned with the orbital velocity of the stars in the outer disk for an extended period, efficiently transferring energy to them. In a retrograde encounter, the tidal forces average out more and the stars are less efficiently accelerated. The Milky Way Andromeda encounter geometry is not yet fully determined. The transverse velocity measurement from Gaia constrains the orbital plane but not all the relevant angles. Different simulations explore the range of possible geometries, and the predicted outcomes span a range of morphologies for the tidal tails and the overall merger dynamics. The first pass itself, the actual interpenetration of the two stellar disks, is, in some ways, the most physically intense phase of the merger, though even it unfolds over timescales of hundreds of millions of years. During this phase, the stars of both galaxies are moving through the combined gravitational field of both systems, their orbits being modified continuously by the changing potential. The gas clouds of both galaxies are compressing, shocking, triggering star formation. The central black holes of both galaxies are experiencing an enhanced inflow of gas, driven by the gravitational torques of the encounter. What an individual star in the inner disk experiences during the first pass is primarily a modification of its orbital parameters. The orbit may become more elliptical. The star may now oscillate more strongly above and below the galactic plane, or its distance from the galactic centre may vary more widely over its orbital period. These changes are not violent from the star's perspective. The gravitational field changes slowly compared to the star's orbital period, which means the transition is adiabatic in the sense that the star's orbital energy changes gradually rather than impulsively. The exception to this is orbital chaos. In the complex, time-varying gravitational field of a merger, some orbits become chaotic, sensitive to initial conditions in the way that limits long-term predictability. Stars on chaotic orbits will have their long-term trajectories become essentially unpredictable, even in principle, because small differences in initial conditions are amplified exponentially over time. The fraction of stars on chaotic orbits increases as the merger progresses, and by the time of the final coalescence, the orbital distribution of stars in the merged system is largely randomized, which is part of why the merger product is an elliptical galaxy rather than a spiral. After the first pass, the two galaxies separate again. This is one of the most counterintuitive aspects of galaxy mergers for people encountering the subject for the first time. The galaxies pass through each other and then fly apart as if the collision didn't bind them. In a sense, it doesn't bind them immediately. The first pass does not have enough energy dissipation to immediately arrest the relative motion of the two systems. The galaxies continue on their modified trajectories after separation, reaching a maximum separation, the turnaround point, before gravity brings them back together for the second pass. The maximum separation after the first pass is much less than the initial separation of 2.5 million light years. Energy has been dissipated through dynamical friction on both the dark matter and stellar populations, reducing the total orbital energy of the system. The galaxies are now on a bound orbit with a much smaller apocenter. The time to the second pass is shorter than the time to the first. The sequence converges. Each pass dissipates more energy, reduces the orbital energy further, shrinks the apocenter, and shortens the time to the next pass. The result is a spiral, not a spatial spiral, but a sequence in time, each pass bringing the galaxies closer, until the separation is too small to sustain the concept of two separate objects, and the merger is complete. The collision of two galaxies is one of the primary mechanisms of star formation in the universe. Not the only mechanism, stars form in undisturbed galaxies all the time, but one of the most spectacular, because the compression of gas by the merger dynamics can trigger star formation at rates far above the quiescent level. The underlying physics is the gene's instability. A gas cloud becomes gravitationally unstable, begins to collapse under its own gravity, when its mass exceeds the gene's mass, which is determined by the balance between gravitational self-attraction and thermal pressure. More massive clouds at lower temperatures are more susceptible to collapse. Less massive clouds at higher temperatures are more resistant. For typical conditions in the cold molecular clouds of the Milky Way, The gene's mass is on the order of a few solar masses to a few hundred solar masses, depending on the local density and temperature. In a normal, undisturbed galaxy, the interstellar medium is regulated by feedback. Stars that form emit radiation and drive stellar winds that heat the surrounding gas, preventing adjacent clouds from collapsing. Supernovae inject enormous amounts of energy into the medium. A single supernova releases approximately 10 to the 44th joules, enough to heat and disperse a large cloud. The net effect of this stellar feedback is to keep the star formation rate self-regulated. The galaxy forms stars. Those stars suppress further star formation in their vicinity, and the overall rate is maintained at a roughly steady level, determined by the balance between gas inflow and stellar feedback. A major merger disrupts this equilibrium in both directions simultaneously. The gas compression increases densities in some regions well beyond the gene's threshold, triggering rapid collapse before feedback can respond. At the same time, the large-scale gravitational torques of the merger drive gas inflows toward the central regions of both galaxies, concentrating fuel in the areas where star formation is most intense. The result is a starburst, a period of greatly elevated star formation that can last for tens to hundreds of millions of years and produce stars at rates of tens to hundreds of solar masses per year, compared to the Milky Way's current rate of roughly 1 to 2 solar masses per year. The antennae galaxies are producing new stars at a rate approximately 10 times the Milky Way's quiescent rate, and some of the most extreme starbursts observed in ultra-luminous infrared galaxies are forming stars at rates of hundreds to thousands of solar masses per year. The new stars formed in the starburst are not distributed uniformly. They form preferentially in compact clusters, superstar clusters, that may contain hundreds of thousands to millions of stars in regions only a few light-years across. These clusters are much denser than typical open star clusters in the Milky Way. Some of them will survive the merger as globular clusters, adding to the globular cluster population of the merged galaxy. Others will be disrupted by tidal forces over billions of years and contribute their stars to the general field population. The starburst produces a biased population. Because the star formation rate is elevated, and because more massive stars form proportionally more from the compressed gas, the starburst produces a large population of massive stars. Stars many times the Sun's mass, burning fast and hot, living only millions of years before ending their lives as supernovae. The supernova rate during a starburst episode is therefore dramatically elevated, which means the rate of heavy element synthesis and dispersal into the interstellar medium is also elevated. The post-merger galaxy will be chemically enriched relative to either progenitor. The massive stars in the starburst region also produce intense ultraviolet radiation that ionizes the surrounding gas, creating H2 regions of ionized hydrogen that glow in the characteristic red light of hydrogen alpha emission. These are visible in the images of the antennae as brilliant knots of pink-red light distributed through the collision zone. Each knot is an HII region lit by a cluster of massive young stars that did not exist before the collision began. The gas that is not immediately forming stars is also being affected. The hot, shocked gas between the galaxies, gas that has been heated to millions of degrees by the shock waves of the collision, is visible in X-ray emission. The Chandra X-ray Observatory has observed this component in the antennae and in many other colliding galaxy pairs, revealing extended plumes of million-degree plasma that are the thermal signature of the hydraulic collision of the two gas disks. This hot gas will eventually cool over timescales of hundreds of millions of years, and some of it will become available for star formation in the later stages of the merger. The dust, the micrometer-sized solid particles of silicates and carbonaceous materials that populate the cold interstellar medium, is redistributed by the merger. Dust absorbs ultraviolet and optical light from stars and re-radiates the energy in the infrared. In the starburst regions, where the concentration of young massive stars and new star-forming clouds is highest, the dust emission is intensely bright in the infrared. This is why many merging galaxy systems appear as ultra-luminous infrared galaxies. The enormous luminosity of the starburst, powered by the gravitational energy of the merger, emerges predominantly in the infrared because the young stars are embedded in dusty clouds that absorb the optical and ultraviolet light. The most extreme examples of merger-driven starbursts are the objects discovered by the Infrared Astronomical Satellite in the 1980s. The ultraluminous infrared galaxies that radiate more than 10 to the 12th solar luminosities, and the hyperluminous infrared galaxies that radiate more than 10 to the 13th solar luminosities. These objects are almost always merging galaxy pairs, and the source of their luminosity is a combination of an intense starburst and often an active galactic nucleus in one or both of the merging systems. The active galactic nucleus contributes because the merger dynamics drive gas inflows toward the center of the merged system, feeding the central black hole and igniting it as a quasar. At peak activity, the quasar can outshine the entire starburst, making the system one of the most luminous objects in the observable universe for the duration of the activity phase. Every large galaxy contains a supermassive black hole at its center. This is one of the most firmly established facts in observational astrophysics, not merely inferred, but directly confirmed for a growing number of galaxies through the motions of stars and gas in the central regions, and most dramatically for the Milky Way through decades of monitoring the orbits of stars within the central parsec, and for M87 and Sagittarius A star through direct imaging by the Event Horizon Telescope. The origin of supermassive black holes is not fully understood. They are too massive to be explained simply as the endpoint of stellar evolution. Even the largest stellar black holes are a few tens of solar masses, while supermassive black holes range from millions to tens of billions of solar masses. The leading explanations involve a combination of initial seed black holes formed in the early universe, either from the collapse of massive early stars or directly from the collapse of massive gas clouds, rapid accretion during periods of quasar activity, and growth through mergers. The merger channel, the growth of supermassive black holes through the mergers of smaller black holes in galaxy mergers, is believed to be significant. The correlation between the mass of the supermassive black hole and properties of the host galaxy's bulge, the M-sigma relation, connecting black hole mass to the stellar velocity dispersion of the bulge, suggests a tight coupling between black hole growth and galaxy growth, consistent with both being driven by the same merger-dominated evolutionary history. During a galaxy merger, the two central black holes initially follow the overall merger dynamics. They are carried by their host galaxies and share in the dynamical friction that drives the galaxies toward coalescence. As the galaxies merge and the stellar distributions reorganize into a single elliptical, the black holes settle toward the center of the merged system through dynamical friction against the stellar background. The early phase of this inspiral is efficient, The black holes are surrounded by dense stellar backgrounds, and the dynamical friction against these stars removes orbital energy rapidly, driving the black holes to smaller separations. This phase brings the black holes from separations of kiloparsecs, the typical nuclear separation after the first galaxy merger, to separations of a few parsecs on timescales of billions of years. Then comes the final parsec problem. The problem is this: as the black holes spiral inward, they eject stars from the central region through gravitational slingshot interactions. A star that passes between the two black holes can be ejected at high velocity, taking energy from the black hole binary and allowing the binary to shrink slightly. This is an efficient energy transfer mechanism when there are many stars available. But the ejection of stars also depletes the central stellar density. The stars are gone, and new stars on appropriate orbits are not replenished quickly enough. The black holes eventually run out of stars to eject, and the dynamical friction mechanism stalls. This is the final parsec problem. The black holes reach separations of roughly a parsec and find no efficient mechanism to bring them closer. Several solutions have been proposed and are being investigated. Gas dynamics may resolve the problem in gas-rich mergers. If the central region retains or acquires a supply of cold gas, driven inward by the merger-driven gravitational torques, the gas can transport angular momentum outward through viscous processes and gravitational torques, drawing the black holes together even when the stellar supply is exhausted. Simulations of gas-rich mergers generally find that gas driven in spiral can carry the binary to separations where gravitational wave emission becomes effective. Stellar triaxiality, the non-spherical shape of the stellar potential in the central regions of merger remnants, may replenish the loss cone. In a spherically symmetric potential, only stars on very specific orbits can approach close enough to the binary to interact with it. But in a triaxial potential, the range of orbits that can access the central region is much larger, potentially maintaining a supply of stars available for ejection long after the loss cone would be empty in a spherical system. The third mechanism, gravitational wave emission, eventually dominates regardless of how the binary reaches the appropriate separation. When the two black holes are separated by roughly 0.001 parsec, about 200 astronomical units, the power radiated in gravitational waves is sufficient to drive the inspiral to completion on a timescale of millions to billions of years, depending on the masses. The final inspiral is rapid, driven by the increasing gravitational wave luminosity as the separation decreases. The merger of two supermassive black holes is an event of staggering energy. For two black holes of 100 million solar masses each, comparable to the Andromeda black hole mass, the gravitational wave energy radiated during the merger is on the order of a few % of their combined rest mass, or roughly several million solar masses equivalent in energy, radiated predominantly over the final years of the inspiral. The peak luminosity in gravitational waves during the final seconds of the merger exceeds the electromagnetic luminosity of the observable universe. The gravitational waves from supermassive black hole mergers have frequencies in the nanohertz to microhertz range, corresponding to orbital periods of years to thousands of years for the binary in its final stages. These frequencies are far too low for ground-based gravitational wave detectors like LIGO, which are sensitive to kilohertz range signals. They fall in the range that can be addressed by pulsar timing arrays, and, in the millihertz range, by the planned space-based interferometer LISA. The pulsar timing array approach deserves more explanation because the 2023 results from Nanograv and its international partners represent one of the genuinely significant observational developments of recent years. A millisecond pulsar is a neutron star rotating hundreds of times per second, with a rotation rate so stable that it rivals atomic clocks in precision. The pulse arrival times of a millisecond pulsar can be predicted years in advance with nanosecond accuracy, given sufficiently precise measurements of the pulsar's properties and the correction of all known effects. Dispersion by interstellar electrons, proper motion, orbital motion, if the pulsar is in a binary system. A gravitational wave passing between the Earth and a pulsar will alternately stretch and compress the distance between them, causing the pulse arrival times to be alternately early and late compared to expectations. The timing residual, the difference between the observed and predicted arrival times, carries the imprint of the gravitational wave. For a single pulsar, a timing residual could arise from many sources: instrumental noise, unmodelled dispersion, errors in the pulsar's ephemeris. But for an array of pulsars distributed across the sky, a gravitational wave background produces correlations between timing residuals that have a specific angular pattern, the Hellings-Downs correlation, that depends on the angle between pulsars on the sky. The Hellings-Downs curve, derived by R.W. Hellings and G.S. Downs in 1983, gives the expected correlation between timing residuals for two pulsars as a function of the angular separation between them. For pulsars in the same direction, the correlation is positive and close to 1. For pulsars at right angles, the correlation is close to 0. For pulsars in opposite directions, the correlation is slightly positive, reflecting the fact that the Earth term of the gravitational wave affects pulsars in all directions but in different ways. This specific pattern, positive correlation at small angles, 0 at intermediate angles, slight positive correlation at large angles, is the fingerprint of a gravitational wave background. It is not the signature of any other known noise source. When the Nanograv collaboration and its international partners published results in June 2023 showing timing correlations consistent with the Hellings-Downs curve across their pulsar timing arrays, the result was widely interpreted as evidence for the gravitational wave background produced by the population of supermassive black hole binaries in merging galaxies throughout the observable universe. The signal is not a single merger, it is the superposition of millions of mergers distributed across cosmic time, each one contributing a tiny gravitational wave signal that, summed across the universe, produces a detectable background. The universe's history of galaxy mergers, billions of years of galaxies finding each other, falling together, merging, is encoded in a nearly uniform hum in the space-time fabric, detectable through the nanosecond timing of spinning neutron stars 1,000 light-years from Earth. A star in the outer disk of the Milky Way is currently orbiting the galactic center at approximately 200 kilometers per second, completing one revolution every 220 to 250 million years. The Sun is one such star, currently located approximately 26,000 light-years from the galactic center in the Orion Arm, a relatively minor spiral feature between the major Sagittarius and Perseus arms. The Sun's current orbit will be modified by the approach and eventual merger with Andromeda. The modification begins subtly and early. The tidal forces from Andromeda will begin to influence the outermost disk stars hundreds of millions of years before the first pass, and the inner disk stars somewhat later. The Sun's orbit specifically will begin to be meaningfully perturbed perhaps 1 to 2 billion years before the first close approach, as the separation between the galaxies decreases to the point where the tidal forces are significant at the Sun's orbital radius. The nature of the perturbation will be gradual and secular. The Sun's orbital parameters will change slowly over millions of years rather than abruptly. The orbit may become more elliptical, carrying the Sun to larger galactic radii on some portions of its orbit. The inclination of the orbit with respect to the disk plane may increase, but the perturbation is not expected to be catastrophic for the Sun's orbital stability on any timescale relevant to the pre-merger phase. During the first pass, the Sun, still on a modified but recognizable disk orbit, will find itself in the combined gravitational field of both galaxy disks. If the Sun happens to be in a region of the disk that is near the interaction zone, it could experience stronger perturbations. If it is in a quieter region of the outer disk, the perturbation may be relatively modest. The stochastic nature of the merger dynamics, the chaotic gravitational field, the changing mass distribution, makes precise predictions for any individual star's trajectory impossible on timescales of billions of years. Current simulations of the Milky Way Andromeda merger include a probabilistic assessment of the Sun's fate. The results suggest several possible outcomes. The most likely outcome, roughly 50% of simulated particles starting at the Sun's current position, is that the Sun ends up on a wider orbit in the merged galaxy, at a larger galactocentric radius than it currently occupies. The merged galaxy is larger than either progenitor, and the overall distribution of stellar orbits is more extended. Roughly 10 to 15% of simulations result in the Sun being ejected from the merged galaxy entirely, placed on an unbound trajectory by the gravitational dynamics of the merger. A smaller fraction result in the Sun being deposited on a much smaller orbit, closer to the centre of the merged galaxy. None of these outcomes changes the short-term fate of the solar system, which is determined by the Sun's own evolution. By the time the Andromeda collision begins, the Sun will have been on the main sequence for approximately 9.5 billion years total, and will be entering the subgiant phase, slightly expanded, somewhat more luminous, beginning the processes that will eventually produce the red giant. Whether any planet remains habitable at that point is determined by the Sun's luminosity evolution, not by the galaxy collision. The night sky that a planet around the Sun would show during the merger is worth describing at some length, because it is extraordinary by any comparison to the current sky. Currently, the night sky shows a diffuse band of Milky Way light, the integrated glow of the billions of stars in the galactic disk, too close and too numerous to resolve individually with the naked eye, appearing as a pale band that circles the sky. The nearest external galaxy visible to the naked eye is Andromeda, the faint oval in Andromeda, the constellation described earlier, currently showing at 2.5 million light-years. Several billion years from now, as Andromeda approaches, its apparent size on the sky grows. At 1 million light-year separation, Andromeda subtends roughly 6 degrees of arc, 12 full moon diameters. At 500,000 light-years, it subtends approximately 12 degrees. At 100,000 light-years, still before the first pass of the galactic disks, it spans more than 50 degrees, filling a significant fraction of the sky, with a galaxy-wide band of light distinct from the Milky Way. At this distance, the individual star-forming regions in Andromeda are potentially resolvable to the naked eye as distinct bright spots. The dark dust lanes of the spiral arms are visible as dark rifts in the otherwise luminous background. The tidal features, the first hints of the tidal tails being drawn out by the mutual gravitational interaction, may be visible as faint extensions of the Andromeda disk into the surrounding sky. By the time of the first pass itself, the sky is unrecognizable from any current reference point. Both the Milky Way and Andromeda's disk span large portions of the sky. The combined system shows tidal tails extending far beyond either original disk, arcs of stars that fill the sky in multiple directions. The starburst regions are visible as brilliant concentrations of blue-white light, far brighter than any star-forming region in the current Milky Way, lit by the tens of millions of new massive stars formed in the compression zones. The two galactic nuclei, the centres of the original Milky Way and Andromeda, are visible as distinct bright regions. If the galactic nuclei are active, if the merger-driven gas inflows have ignited the central black holes as active galactic nuclei, they would appear as extraordinarily bright point sources or compact regions, potentially as bright as Venus or brightest to the naked eye, depending on their luminosity and distance. An active galactic nucleus radiating at quasar luminosity, even at a distance of tens of thousands of light-years, is one of the brightest possible objects in a sky. The starburst elevated supernova rate would mean that supernovae, rare events in the current Milky Way, occurring perhaps twice per century, would occur much more frequently during the starburst phase. Supernovae visible to the naked eye, events that historically produce bright new stars in the sky for weeks to months, might occur multiple times per century, or even multiple times per decade during the peak of the starburst. The sky would occasionally host brilliant transients, stars that appear suddenly, brighten to Venus-like or even moon-like brightness over days to weeks, and then fade over months. The radiation environment during the starburst phase is worth considering separately from the visual appearance of the sky. The elevated supernova rate means an elevated rate of gamma ray and cosmic ray production. Supernovae are significant sources of both. The current cosmic ray environment at Earth's surface is largely shielded by Earth's magnetic field and atmosphere, but a significantly elevated cosmic ray flux could have consequences for atmospheric chemistry and potentially for biological systems. Whether the increase would be catastrophic depends on the distance of the solar system from the starburst zones and the geometry of the merger at the relevant time. If the Sun ends up on a wide orbit that takes it through the outskirts of the merged system during the starburst phase, the radiation environment may be little different from the current one. If it ends up in a more central location, in or near the starburst zone, the radiation environment could be significantly different. The probabilistic nature of the solar system's post-merger orbit makes precise statements impossible. After the merger is complete, after the billions of years of dynamical settling have produced the final elliptical galaxy, the sky changes again. The extraordinary complexity of the merger sky gives way to something simpler and quieter. The elliptical galaxy presents a smooth, featureless distribution of old red stars in every direction. There are no prominent spiral arms, no brilliant star-forming regions, no tidal tails. The sky is more uniform, the integrated light of the stellar population distributed without the clumping and structure of a spiral disk. The star formation rate is very low. Most of the cold gas has been consumed. New stars are forming at a rate far below the pre-merger levels. The brilliant blue-white star-forming knots that lit the starburst sky are gone. The massive stars that produced them lived only millions of years and have long since evolved and died. What remains is an older, redder population. The night sky of the final merged galaxy, seen from a planet around a star that survived the merger intact, would be beautiful in a different way from the current sky or the merger-era sky. Less spectacular, less varied. The diffuse glow of billions of old stars in every direction. Quiet. Old. The product of an event that took billions of years to unfold. A merger is complete. There is no event that marks this. No moment at which the system transitions from two galaxy to one galaxy. The distinction dissolves gradually over billions of years as the tidal tails disperse, the star-forming gas is consumed, the stellar orbits randomize, and the two original nuclei lose their separate identities in the combined stellar background. What remains is an elliptical galaxy. The naming of the type is almost too simple for what it describes. Elliptical means smooth, featureless, roughly ellipsoidal in three-dimensional shape, lacking the disk structure and spiral arms of the progenitors. The physical reasons for this shape are what the merger has produced. The rotational order of both original disks has been destroyed by the tidal interactions. The gas that maintained the disk structure has been consumed in the starburst, and the stellar orbits now form a three-dimensional pressure-supported distribution rather than a rotationally supported disk. Elliptical galaxies are among the oldest objects in the universe. Their stellar populations are dominated by red giant stars, stars of moderate mass that have completed their main sequence lives and are now expanding and cooling into the giant phase, and lower mass main sequence stars that age slowly and can persist for tens of billions of years. The blue, short-lived massive stars that characterize star-forming regions are absent because there is no new star formation to produce them. The colour of an elliptical galaxy, reddish, compared to the blue-tinted light of a spiral with active star formation, is literally the colour of age. It reflects the statistical distribution of stellar luminosities in an old population. Most of the light comes from red giant stars and the cooler end of the main sequence, with no contribution from the hot massive stars that dominate the blue end of the spectrum in a starburst. The metallicity of the stellar population, the abundance of elements heavier than helium, produced by stellar evolution and dispersed by stellar winds and supernovae, is typically higher in elliptical galaxies than in spirals of comparable mass. This is partly because ellipticals have processed more gas through star formation. The multiple merger-driven starburst events enrich the medium, and partly because the lack of subsequent star formation means the stellar population reflects the enriched state of the gas at the time of the last major star formation episode. The supermassive black hole at the centre of the merged galaxy is the combination of the two original black holes, minus the mass radiated away as gravitational waves during the merger. The merged black hole sits at the centre of the elliptical, largely quiescent. The merger-driven gas inflow that briefly ignited it as an active nucleus has been exhausted, and the central region is relatively gas-poor. The black hole will continue to grow slowly through accretion of the residual gas and through tidal disruption of stars that wander too close to the galactic centre, but its period of peak activity is over. The globular cluster population of the merged galaxy is the sum of the two progenitor populations, modified by the formation of new clusters during the starburst phase. Large elliptical galaxies particularly those at the centres of galaxy clusters which have undergone many mergers, typically have large globular cluster populations. The globular clusters are among the oldest intact structures in the universe, their stars having formed 10 to 13 billion years ago in the high-density regions of early galactic mergers and surviving intact for the entire subsequent lifetime of the galaxy. Looking at the globular cluster population of an elliptical galaxy is like reading a geological record. Each cluster encodes information about the conditions that formed it, when and in what merging event. The chemical record embedded in the individual stars of the merged galaxy is similarly archival. Each star's atmosphere preserves the chemical composition of the gas from which it formed. Stars that formed in the original Milky Way carry the nucleosynthetic history of the Milky Way's star-forming episodes. Stars that formed in Andromeda carry Andromeda's chemical history. Stars that formed in the Starburst carry the elevated metallicity chemistry of the collision zone gas. In principle, and to some extent in practice through detailed spectroscopic surveys, these populations can be separated even billions of years after the merger, because the chemical signatures are different enough to distinguish. The Milky Way's current stellar population already contains multiple chemically distinct components that reflect its merger history: the thin disk, the thick disk, the halo, each with different age and metallicity distributions that reflect different formation episodes. The merged Milkomeda Galaxy would be far more complex chemically, reflecting the superposition of the star formation histories of two major spirals, plus all the satellite galaxies absorbed by both over their lifetimes. The structure of the merged galaxy is not perfectly smooth. The scrambling of stellar orbits is thorough, but not instantaneous, and remnants of the original structures, shells of stars, kinematic substructures, regions of slightly different chemistry or age, persist for billions of years after the merger. These substructures are the equivalent of the streams and overdensities visible in the Milky Way's current stellar halo. Ghost structures from past mergers, gradually dispersed by the gravitational potential, but readable by sufficiently detailed surveys. Large elliptical galaxies that have undergone significant merger histories often show shell structures in their outer regions, faint arcs and fans of stars that the remnants of tidal streams from absorbed satellites, maintaining coherence in phase space, position velocity, long after they have dispersed in physical space. The Hubble Space Telescope and its successors have revealed these shells in extraordinary detail in nearby ellipticals, providing direct evidence of their merger histories. The universe has been colliding with itself for 13 billion years. Galaxy mergers, large and small, between comparable masses and between giants and dwarfs, have been happening since the first galaxies assembled in the first billion years after the Big Bang. The rate of major mergers was higher in the past when galaxies were younger, more gas-rich, and closer together in the smaller early universe. But mergers have continued throughout cosmic history and continue today. The accumulated gravitational wave signal from all these mergers, the billions of supermassive black hole binaries that formed in merger remnants, slowly spiraling together and eventually radiating their orbital energy as gravitational waves, constitutes a background of gravitational radiation filling all of space. This background has been building for billions of years. It is, in a sense, the acoustic record of the universe's structural history. The sound of matter finding its way into larger and larger structures through the patient operation of gravity. And in 2023 we heard it, the nanograv collaboration, along with the European Pulsar Timing Array, the Indian Pulsar Timing Array, the Parkes Pulsar Timing Array, and the Chinese Pulsar Timing Array, working independently and jointly, published results showing correlations in pulsar timing residuals consistent with the Hellings-Downs signature of a gravitational wave background. The result was the product of years of data collection. In the case of nanograv, approximately 15 years of timing data on dozens of millisecond pulsars distributed across the sky. The technical achievement behind this result deserves recognition. Millisecond pulsars are extraordinary objects. Neutron stars rotating hundreds of times per second, products of the accretion of matter from a binary companion that spun them up to these remarkable rates. Their rotation rates are stable enough to function as the most precise natural clocks in the universe. The timing precision required to detect the gravitational wave background is at the level of nanoseconds, billionths of a second, over baselines of many years. Achieving this precision requires modelling and removing every other known source of timing variation, the proper motion of the pulsar across the sky, the orbital motion of the Earth around the Sun, including relativistic corrections, the dispersion of the pulsar's radio signals by the varying column of interstellar electrons along the line of sight, the intrinsic spin down of the pulsar due to magnetic dipole radiation, and many other effects. What remains after all these corrections, the timing residuals, contains any signal from gravitational waves if one is present. The 2023 results showed timing residuals with two key features: a common spectral shape across all pulsars, consistent with a gravitational wave background with the expected power law spectrum, and angular correlations between pulsars consistent with the Hellings-Downs curve. The angular correlation is the key signature. It is what distinguishes a gravitational wave background from a common noise source affecting all pulsars identically. The Hellings-Downs curve predicts positive correlations between pulsars separated by small angles, decreasing correlation at intermediate angles, and a slight positive correlation at large angles, reflecting the geometry of how a gravitational wave background affects the Earth pulsar distance for different pulsar positions. The 2023 data showed these correlations at a significance level that the collaborations characterized as strong evidence for a gravitational wave background, while noting that the interpretation in terms of supermassive black hole binaries is the most natural but not the only possible one. Alternative explanations include exotic early universe processes, phase transitions, cosmic strings, primordial gravitational waves from inflation. Distinguishing between these explanations requires more data and more detailed spectral analysis. But the most parsimonious interpretation, the one that requires no exotic physics and is consistent with the expected signal from the known population of galaxy mergers, is the supermassive black hole binary background. If this interpretation is correct, and the growing weight of the data suggests it is, then the 2023 Pulsar Timing Array results represent the first detection of a gravitational wave background from the cosmic population of merging galaxies. Every galaxy merger that has produced a supermassive black hole binary that subsequently merged has contributed to this signal. Billions of such events over billions of years, each one producing gravitational waves that travelled across the universe at the speed of light, arriving at Earth as an ancient attenuated signal from a cosmic process that completed long ago, summing with all the other signals into the correlated timing variations that Nanograv and its partners measured. The universe has been merging galaxies since its earliest epochs. and the gravitational echoes of those mergers are arriving at Earth right now, encoding the history of cosmic structure formation in the nanosecond timing of spinning neutron stars. There is something about this that resists being said simply, because it involves a kind of scale crossing that the mind does not naturally perform. The signal being detected is ancient. The supermassive black hole mergers that dominate the background are distributed across cosmological distances, with the dominant contribution coming from mergers at redshifts of around 1 to 2, corresponding to look-back times of roughly 8 to 10 billion years. These are mergers that were completing when the Sun had not yet formed, when the Milky Way was less than half its current age. The waves from these mergers have been travelling for 8 to 10 billion years. They've been crossing the universe while the Sun formed from a molecular cloud, while the planets coalesced, while life appeared and evolved, while multicellular organisms developed, while the Cambrian explosion occurred, while vertebrates colonized the land, while dinosaurs dominated, while mammals inherited the earth, while primates evolved, while hominids arose, while humans developed language and technology, and eventually radio telescopes and millisecond pulsar timing. And then, in 2023, we measured them, in the timing residuals of spinning neutron stars, at nanosecond precision. The Andromeda Galaxy is 2.5 million light-years away and approaching at 110 kilometers per second. The collision will begin in approximately 4 to 5 billion years. The merger will produce gravitational waves from the eventual coalescence of the Milky Way's 4 million solar mass black hole with Andromeda's 100 million solar mass black hole, an event that will take place perhaps 6 to 8 billion years from now, producing gravitational waves in the nanohertz frequency range that will propagate outward from the merged galaxy for billions of years. If, somewhere in the universe, there is a civilization that has developed pulsar timing arrays and that has a collection of millisecond pulsars within reasonable distance of a future Milkomeda, they may detect, billions of years from now, a signal from our galaxy's merger, one entry in the background hum of gravitational waves from a universe full of merging systems. They will not know it is us. The signal will be too distant, too attenuated, too mixed with other signals from other mergers. But it will be there. Our collision encoded in the fabric of space-time, travelling outward in all directions at the speed of light for as long as the universe exists to carry it. There is a different scale at which to consider this, and it may be the most appropriate one for ending a video like this. You are somewhere at this hour. The building you're in is made of atoms that were synthesized in stellar interiors, carbon, oxygen, silicon, iron, processed through generations of star formation and stellar death and supernova dispersal, assembled by gravity into a planet, further processed by geology and biology into the materials of the constructed environment you occupy. The atoms in your body have the same provenance, and those atoms, your atoms, assembled into you, in a room, at this hour, are embedded in a gravitational field produced partly by the Andromeda Galaxy, 2.5 million light-years away. The field is tiny at this distance. The acceleration it produces on your body is something like 10 to the negative 13th meters per second squared, unmeasurably small, far below any threshold of detection. But it is real. It exists. You are, right now, being attracted toward Andromeda by a force that has been acting since the Andromeda Galaxy and the Milky Way first became close enough to exert a detectable mutual pull. You're falling toward another galaxy. The fall is imperceptible. The fall has been happening your whole life, and the lives of every human who preceded you. The fall will continue for 4 to 5 billion years before anything dramatic happens. But the fall is real, and somewhere in the timing residuals of millisecond pulses distributed around the galaxy, in the nanosecond deviations from expected pulse arrival times measured by radio telescopes on Earth, the accumulated record of every fall like this one in every merging galaxy system across the observable universe over the last 13 billion years is being written, very slowly, in nanoseconds,